We said that an int is 32 bits. It's 4 bytes. So we divide this by 4, and we get how many integers we can store. All good? And what's that? Okay. So you can do it that way. Because we have 512, and 12 split by 4, that's 128, and multiplied, and that's how many integers we can store. As you can see, the program that you wrote today wouldn't even dent the amount of RAM that we have in the microcontroller. Okay? We have a lot of RAM for stuff like this. But it's important that you know the size of the stuff that you're storing. Because otherwise, you can empty, or you can fill the whole RAM of the microcontroller if you're not careful and you don't understand what you're doing. Okay? And this also affects speed. We will be using this include. Okay? This include allows us to have standard integers that work everywhere that have fixed sizes. Okay? If, for instance, we are working with values that we take from the reality, and we take, I don't know, we need to sample 1,000 values of what a sensor gives us, we can estimate which size would be the best to accommodate it in RAM and not use as much as needed. Okay? If the sensor can only give us 4 values, we can use a byte to store it instead of using an int32 and wasting a ton of RAM. Okay? How is that defined? It's defined with this type of variables. Instead of using a pure int, we can use an unsigned, that is, it has no sign, integer of 8 bits, and this is just type. Okay? This tells us this is a type. So this is an unsigned integer with 8 bits. And that gives us values from 0 to 255. Okay? We know that. If I type int 8 underscore t, that is minus 128 to 127. Okay? So I have that range. If I do int 16 underscore t, that means an 8-bit number or a 16-bit number. That's a 16-bit number. Okay? We can store double the amount of these numbers in RAM if we use 60-bit. We can go up to 256 times this. Okay? But it all depends. If we need numbers bigger than 2 to the 16 minus 1 minus 1, then I go over to int32, right? So I have to pick up the size of the variables that I'm going to store in memory, depending on how much memory I have and how much memory I know I need for the data to be able to be stored. Okay? All good up to this point? We also have, as I mentioned, int16. This is the values on the range that it goes, right? We have int32. Okay? So we have a lot of variables that we can define. And each one of these changes the way that we use memory. And also changes the range of the values that we can store. If we are not careful and we store values, for instance, in this kind of variable, I cannot store the value 40,000. That can't be represented inside of that variable. Okay? I would need to go to an int32 to represent that kind of variable. Good? Or I could go with int16t, and that way this goes to 64,000, right? And I could use that to store this value. But I need to know the type of the data that it has coming from the outside or from my calculations. I need to be able to determine its range. Okay? Any questions about this? All good? Yes? So, if if I want to store a value of minus 60,000, would an unsigned int 16 work? Would that work? Would that work? But you can tell me for certain. Hmm?
For certain.
For certain numbers, that's the case. Okay. So, what would this be? You can tell me also what's the range of this variable, right? And again, you don't even need to pick out a calculator and calculate it. You can tell me it's 2 to the 32 minus 1, right? 0 to 2 to the 32 minus 1. That would be the range. And yes, you can take out the calculator and check if that is true, right? If that works for you. All good? As you can see, here we have the int64. This, try never to use it in the microcontroller unless you need to use it. Okay? You have to be certain that you need to use it because this has no hardware support. This is all made by software, and that makes it slower. But it's very good to have something like a timer. Use this that you will only be using once every cycle. Okay? But never use all your variables as int64 because you're going to spend double the memory and more than double the speed of the CPU. Okay? But as you can see, the range is incredibly large. Okay? All good? Now, we'll talk about bitwise operations. This is quite important for you because it's used to pipe data or extract data from within variables. Okay, this can be used with certain kind of sensors, but it also can be used for our purposes to split data and send it in chunks. Okay? But also we can use it to mask data. I'll tell you what that means. Have you ever spray painted something? How do you do it? You make a
Canvas.
You use a canvas, but what did you make with masking tape? Yeah, we make a mask. We make a mask that masks everything that we don't want to paint. Okay? Then we paint it and remove the mask, and only our stencil leaves the mark of what we need, right? That's kind of what we're gonna do with bitwise operators. We can create this kind of masks and clean certain parts of a variable and get just the information that we want, okay? We'll be talking about that. First example is this. It's the AND. Do you know the symbol from other uses in C so far? What have we used it for so far?
Address.
An address, yes. And to scan, that's the address. So for a scanf, we need the address of the variable to store it. So you're talking about the same thing and it's good. What else have we used that symbol for?
The AND operator.
And the AND operator. But how was it written?
Double ampersand.
And it feels kind of backwards to me to teach you this way, because this is more fundamental. That's why it's on the same one, right? C was designed to be a hardware programming language, and that's why this is more important to have it as a symbol for AND operating at the hardware level. And this is for a logical level. If you use this, the result of these two variables would be true or false, right? But if you use this, the result of both variables would be 0 or 1. All good? We'll see it with more detail here. This example, as you can tell, I'm using already the standard integer. That's how you can remember how to import this. Okay? You import the standard integer library. And this brings uint8 or uint16, etc. These numbers can only store values up to 255. All right? Why? Because they are 8 bits, and they are exactly this. This 12 is this. This 7 is this. Okay? Well, cool. And what's the result of the AND operator? I'm making an AND between A and B. Okay? What's the result? It's very simple. 0 and 1, 0. 0 and 1, 0. 1 and 1,
0,
1.
1.
And then you go. As you can tell, this mask is exactly, we're using it like a mask right now, right? This number masks this one, and only what's masked goes through. Okay, this will be more clear in a bit. Let me show you a couple of things. Oh, any questions regarding this slide? Do you know every single letter in that slide? Or do you have a question regarding one of them?
Yeah, the format specifier, what about the lowercase and uppercase x?
Yep. There's something strange there, right? I'm gonna make it a bit easier. In reality, this is not part of the format, and this is not part of the format. That's just text. I'm doing this. So far, I told you half truth. I said that for ints, you use D. Did that make sense? Yeah, but why not an I? It doesn't. No, we use D because that's decimal. We are printing in decimal. And the X is printed in hexadecimal. Okay? That's why it was D. D is for printing in decimal. And X is for printing in hexadecimal. Okay? Now it kind of makes more sense. And it'll be harder to forget what to use when. Because if you want to print decimal, you use D. I can tell you in advance, you're probably going to be using hexadecimal a lot. Okay? And this is just format, so I can output this, and the person that's reading it understand that it's hexadecimal because I placed an X. Okay? Let's run this code and make some changes so you can see what I mean. Okay? We have this code, and we're going to make a few changes, a few interesting changes. If I write, what's that? What change did I make? You can tell that I changed the 12 for 0x, 0c. This is the exact same thing. 12 is C in hexadecimal. Remember?
Yes.
Yeah? So this sometimes is more clear when you're working with hardware, because you know that a C is this pattern of bytes, or bits, sorry, 1100. You know that immediately with experience. Okay? Same here. You know that that is a 4. Okay? And that's why we use hexadecimal when we code in hardware, because it makes it easier to read the binary immediately. Okay? Obviously, you need to know, memorize, and have experience. But that's why we do that, because it's easier to identify these patterns. Just memorize 15 patterns, and you can read all binary grouped as hexadecimal, right? Just as if I do this, and we'll talk about that. That's an hexadecimal now. And you can see that this letter corresponds to that hexadecimal. You don't need to learn those. You can remember from what we learned a few sessions ago. But let's just play with this a bit. Okay? Remember, programming is like playing with toys. Try to think about it that way. These are toys, okay? And we're gonna play with them, and from playing with those toys, we'll learn some things. First of all, if I do this, did the code change at all? It's
And
it shouldn't care because 7 is 7 in hexadecimal and in decimal. Okay? That's the exact same code. All good. If I change this to this, think about it carefully. Will it change? What am I doing with that? What does that mean? Of course, these comments with the numbers are not exactly true, right? What are they now? They are bigger. What's in line 5? What does it say in line 5? How many bits can I store there? How many bits are here? Think about it carefully. It feels like 4, right? Let's go back to this. How many bits are there here? Remember something, okay? What's this? This is 0, this is C. Every character is a byte, yes. But here we're talking about a number, okay? And these numbers, what are they?
One, two, three.
Yeah, let's keep on moving. Let's leave those, and now this. What are these?
8, 9,
Huh? And the next one?
A, B, C.
There you go. These are C. Okay. 9, A, B. No. This was 8.
Yes.
9, A, B, C. Okay? This is true. So, this, how many bytes is this?
4.
Right now, how many bytes is 0C? 2 bytes? How many bits did I need to encode the C?
1.
Bits for a C? How many bits do I need to encode the C? Here. For the C, how many bits do I have? 4. Okay. How many do I have in a byte? 8. So this 0 is half a byte, and this C is half a byte.
This one.
Just 4 bits. That's called a nibble, okay? So if, now that you thought about that, I go back to what I showed you. What happens with that code? Will it change? The result was 4 beforehand, right?
Mm-hmm.
Why was it 4? Because I do an AND operator over these two. The only one that the mask allows to pass is this, and this is 4. Okay? Will it change if I add this? Or will it be the same? How many bytes are there in that number that I wrote? Let's build it, and let's run it. You see, because I have certain flags turned on the compiler, I told the compiler, give me all warnings and be pedantic, okay? And since I told him that, it says, hey, you're converting an int to a uint 8. That doesn't fit, okay? Let's remove those warnings. It still lets me know that I made a mistake, okay? But it compiled. What happens if I run it? It gives me 4. Surprised or not? Why? Because I told it to store this inside a byte, but this doesn't fit, so this gets thrown away completely because it doesn't fit. Okay, this is why it's important to understand what you're doing. Okay, and how big the variables are, and how much is a byte. Okay, that's why it's important, because you can be making mistakes when you do that. Okay, all cool? And that's why we write in hexadecimal a lot, because it's very easy to find this kind of errors. If I have 65,000 written there, it would be hard to find. And this way, I have an uint 8, and I'm storing a uint 16. That won't fit, right? Because this is 2 bytes. This is a uint 16. All good? No questions?
So it's 4 bits? So it's 8 bits.
Which one is 8 bits?
The other one.
This?
No, the other one.
16 bits.
What?
4, that's 8. 4, 16.
Correct.
Yeah? Because this, you only need 4 bits to encode each one. Okay? Yes?
I don't understand why when 0 export.
When?
Why is that
0, 4? Sure. Do you agree that, let me erase this so it's not confusing. Do you agree that 0C is this? Yes? And 07 is this, right? 0 and 1? 0. 0 and 1? 1 and 1? 0 and 1? 0, 0, 0, 0. What number is this one? Okay. If you're trying to figure out a mathematical meaning to this, this is not mathematics. This is binary logic, right? There are certain operations that do have a mapping to mathematics, and we'll learn about them in a minute. I'm just spending this time here because it's important that you understand all the basics before we move on to the next operators. Okay? All good? Remember that these samples, this sample code that's in the presentation in the slides, you can download a text file that has every single example so you can play with them. Okay? They are in Canvas. So we move here. What do we have? The OR, no surprises there. It's a single type. Okay? The XOR, it's that accent. Okay? So whenever that happened to you in the first practices that you wrote 2 to the 4, you were not writing 2 to the 4. You were writing 2 XOR 4. Okay, that's what that means. You are doing an XOR over the bits in those 2 numbers. If you write that, it compiles, yes, but that's because you're doing a different operation. This is not power. Okay? And this is not. Here are some examples. We have the same 2 numbers, okay? We do an OR, and this is a result of an OR. Okay? This is the result of an OR. This is the result of the XOR. So this is the exclusive OR. 0 or 1, that's 1. 0, an exclusive OR 1, that's 1. 1 XOR 1, that's 0. Okay? And so on. And if we do a NOT operation, that's basically complement to 1. We flip all the bits. So we have A, which was this 12. If we flip all the bits, we get this. Okay? Every single bit flipped. There you go. Okay? Any questions? No? Good. We're going to be using them a bit more. There's a couple more bitwise operators that are very important. Okay? This is shifting to the left. Did you build a flip-flop and you started storing bits inside of it? A register and started shifting values? Yes. This is exactly that, but in C. We're shifting values. Here we have this 12, okay? If I tell A, shift twice to the left, this is what it means. to the left and I shift twice, these two move. Not just the ones, everything inside of the variable shifts to the left, 2 spaces, okay? And any numbers that come in, they are always 0, okay? If I would say shift 12 places to the left, what would be the result? Zeros, all zeros, okay? Those 2 ones, they get lost because we are storing in a uint 8. It overflows and it goes to nothing, okay? And the same with shifting to the right. Now, see that you can use that exact same syntax as we did with the plus or with the minus, okay? You can combine. This thing is the exact same thing as doing a shift twice to the right, okay? This is just more compact, okay? Questions? Oh, good. Now, one important thing, very important thing. What happens if I have a 4 shifted 2 to the left? What's the result of that? Let's go. We have a 4. 0, 1. And if we shift that 2 to the left, what's the result? Right? We are multiplying by 2 times. That's what it does. Because we are shifting the position of all ones to the left. Okay? Every single bit that we move to the left, we are multiplying ones by 2. Okay? And if every single time we shift something to the right, we are dividing by 2. So this is a very fast way to make division or multiplication only by 2, by factors of 2. Okay? But this is very cheap in CPU time because this is a single cycle operation in the microprocessor or microcontroller in our case. Okay? As opposed to division. Division is slower. This is faster. Okay? But it only applies for powers of 2. All good? And now, one important thing. It doesn't mean that you shouldn't write like C divided by 2. You can perfectly do that. And modern compilers will turn that into a shift by themselves. Okay? So you don't need to make things cryptic just for the sake of it. But when you want to, do it precisely. Okay? No questions regarding this? Yeah? Okay. Now, we'll talk about the masks that I was telling you about. This, I called it a mask, but this is just the name of a variable, right? But I'm building a mask. I'm building it, I say 1 shifted to the left 3 times. That will give me this mask. It's very useful to write it this way, because that way you can tell immediately that this number is this mask, okay? If I wrote an 8, it won't be as clear to someone that this is the 4 with the 3rd bit turned on, okay? That's why we usually write it that way, because the compiler will transform it into an 8. Okay, it won't cost us anything at CPU time when it's executed. It's already built. But it's very clear in terms of documentation that it's telling it, create this mask. Okay, create a number that has this bit, the 3rd one, turned on. That's why we usually do it. Okay? Now, here, this code just makes a shift to create a mask. It's a different mask than the one above. Okay? It's 100 instead of 1000. And I simply use the mask. The mask lets through only this one. All the other zeros with the AND, they go. If they were zeros, they are kept as zeros. If they are ones, they are zeros. Okay? That's why it's very similar to a mask in a stencil that you use to paint. Okay? It goes through. And you use this mask to select. I just check, is that not 0? I don't need even to check if it's an 8. It doesn't matter. I just check if it's not 0. If it's not 0, then the bit is sent. Okay? And I can print this. I wrote it on purpose because it's very common that you will be seeing this. I don't enforce that you use this. You can use an if, and it's the exact same thing. This is an if. If bit is set, then true. Else, false. It's just a more compact way, and you will be seeing it everywhere because we engineers love to do that, but it's not very clear to someone that sees it from the first time, okay? But that's it, it's just an if. It asks, is this true? If this is true, then whatever is after the question mark is executed. If not, this. And it's for single statement code, okay? Never use it for an extended piece of code. All good? Questions? Good? Yes? Yes? Okay. Well, let's keep on moving. Because we have more binary masks. As you saw, when I created a mask and used the AND, it was used to check if a bit was set. That could be something that I just taught you, and you said, okay, I use this mask for this, but I'd rather have you understand how to build them and why they work. This sets specific bits, okay? Or sets specific bits. Why? Because zeros pass as they are. Ones pass as they are. But when I have a 1 here, it passes as a 1. Okay? I can use a mask and an OR to set bits in a fashion. Okay?
Teacher, I have a question. Why do we do like the shifting instead of just writing like a 2?
Because it's clearer to see how many bits is shifted. Because this is a very simple mask. But imagine it's a 64-bit number and I want to set bit number 17. Yeah, you see why? So I would write just 17 on a 32-bit number. And what number is that one? That's harder to tell, right? 2 to the 17. That's it. But that's why we do it this way, because it's easier to maintain. If the specification changes and they tell you, now it's bit 7, you don't have to transform that to a number and go back around and change it, right? You just change this number. And it's clear, that's why, okay? And it has no cost of execution time because this is calculated by the compiler, not by the microcontroller. Okay? These are fixed operations and they are calculated at compile time. Okay? And below, we have the and not. We can use this combination to clear bits. Here, I create a pattern that's turn on the 3rd bit. I flip it with negation. I arrive to this. And if I use an AND, every single bit passes through, but the one that I'm asking for. Okay, that one is set to 0 always. All good? Okay. Now, you can toggle bits with XOR. This will be the last one of this. Okay? XOR, exclusive OR, toggles a bit. If it was on, it gets turned off. If it was off, it gets turned on. Okay? Why? Because XOR 1 is 0. If they match, it's 0. Okay? If we have both zeros, 0 XOR 0, what happens?
Zero.
That's kept. So only the ones that we are setting in the mask get flipped. You see? These are kept. And this, since I placed a 1, if it was a 1, it turns into a 0. If it was a 0, it gets turned into a 1. Okay? All good? Now, what does this code do? You can now understand this code fully. Take your time, okay? And tell me what it does. Yeah. It's the third bit if we start counting since we are but I see what you mean. Si estos dedos, digo, no, ahorita vamos a volver eso. Y este cero. Esos son 10 números. Cero. Y estos con sus ingresos son cero. Lo mismo pasa acá. Por eso de hecho empieza siempre. Porque si haces shift 1, entonces shift 0 y se queda por eso. Por eso let's follow it, okay? Let's follow it by hand. Okay, I received two values here. This is the exact same code from last example. I'm just printing each number calling this, okay? I say print binary of value. This is 0, 0, F. It'll be more interesting if I do this. Well, it'll be the same, 0, 0, F, okay? So I receive 0, 0, F. 0, F. Okay? The first thing that happens here is that I create a variable that's called number, okay, that has 0, F. What happens next? I say bit count equals, so I create a new variable that's called bit count. Size of number. You don't know what that is, right? Size of sounds like it tells you the size of something, right? And yes, that's what it is. It tells you the size in bytes of something. So size of number is
8.
bytes.
4.
1. 1. Hmm?
What?
How many bytes is a bit? How many bits is a byte?
How many what?
Bits is a byte.
4.
8.
8.
8 bits is a byte.
Okay.
Yes? So if 8 bits is a byte, this gives us 1. Okay? If I told it uint 32t, what would be the result of that size of? 4, exactly. That would give me 4. Okay? If I gave it an uint 64, it would give me 8. Okay? If I told it uint 16, it will give me 2. So what I'm doing is I'm checking the size of this variable and multiplying that by 8 because that's the number of bits that I need. Okay? So what does it do then? Here I store 8. That would be the result. Okay? And then starting from I equals to bit count. Okay? But I subtract 1. I starting from 7. Okay? And I ask, is 7 bigger or equal than 0? Yes, it is. Then execute this. The number that we have, okay, I shift it to the right. How many times? I times. So I have this number that's 0f. Okay? What's that number in binary?
16.
Okay? That's it, right? If I shift it to the right 7 times, what happens?
0.
This is 1, 2, 3, 4, 5, 6, 7. Okay? All zeros. You follow that? We're all zeros. And I end it with a mask of 1. A mask of 1 is simply that. I aligned them this way, right? And I'm asking, what's the result of this AND? Is it 1? Is it? What's the result of this AND operation? 0. So the if is false, so I print 0. Okay? I do that 4 times, and they will be zeros. Then I ask 4 times 3. Okay? I ask the number, this number, shifted to the right 3 times. 1, 2, 3. Okay? Is this and 1? 1? It is. I print a 1. And I go on printing once. And I just print enter. You see how that works? All good? Let's run it. And you can see what it prints, okay? It prints, this is 0F, and now this is that mask that I created. There it is. It's 3 flipped. And this is a result of the operation of the AND between 2, okay? And I'm showing you this for several reasons. First of all, so you see them applied to something that you can use right now. Second, so that you are not afraid to write this kind of code, okay, and get familiarized with it, because you will be doing this kind of thing sometimes. I don't say all the time. Back in my day, when we coded hardware, we had to do this all the time, right? But now you'll have to do it seldomly, but you'll have to do it, and you'll see code like this, okay? And you need to understand what you're doing. Okay? So remember, practice this material as well, because it's going to be useful for a lot of things. Okay? Any question on how this works? No? Now, that was it for bitwise operations, okay? We got the basics. We now know how a print works. Printing a number, when you say printf %d, this is the kind of thing that happens inside the computer. It grabs the number, takes it by parts, split it in between tens, and printing the numbers. But it has to do that to transform it into decimal. That's what that %d does. Okay? It's quite simple, as a matter of fact. It's not very different than this. Instead of, this is a division by 2, after all. Okay? It does division by 10, and then prints whatever is left. That's what it does. And it will be kind of the same thing. Okay? Now, this code, we're going to talk about the switch statement now. This is something that you'll be using a lot for your state machines. This is the way that we're going to be transforming our state machines into code with switch statements. There's a lot of reasons on why, but the first one that you need to know is that this is faster than using ifs. I can explain it to you why, if you want to, but it is faster in the microcontroller, okay? Because it doesn't need to check every case. What it does is checks a case and adds a number and jumps to that number. So it doesn't check this and then this and this. No, it jumps directly to the number. So that's faster than having 10 ifs. If you have 10 ifs in the microcontroller, it needs to go and check each one of them. In this scenario, it doesn't. It jumps to the position that you tell it to. But this only works with numbers and characters. Okay? It doesn't work with floats, doesn't work with strings. Okay? It does work on negatives if you have, and if you want. But it's basically numbers. Because, as you know, chars are numbers. Okay? I just place them for completeness. But in reality, it only works in numbers. What's the structure? You have the switch statement the variable in which you want to operate on, and then you have cases, each one with a value. Okay? And the value executes these sentences that are in between the case and the break. You need to place a break if you want to stop there. We're going to learn a bit more about that. And one important note, if you declare variables inside of this code, use the curly brackets. Okay? Here is your note, so you remember. Otherwise, you'll find yourself with bugs that are hard to trace. Okay? Questions? Let's see some examples. What would be the output of this?
1.
1. Any other suggestion? Just match what I just taught you about the structure with this that you're seeing. You can go again here. What's the structure on the right? And the example I'm giving you. Does it match?
The break is missing.
The breaks are missing. Okay? Let's see what happens when I run this. What was the output? 1 and 2. Why? Because the code falls through. That is, I told it, when you receive a 1, jump here. Jumps here, executes it, and goes on executing until it finds a break. Okay? That's how it works. And you might ask me, why is it made that way? Where I can make mistakes, right? Because it feels as if this is purposefully made so that I can make mistakes. That's not the case. This gives us freedom. What would be the result of this other piece of code? This has a Z. It matches the C. Is it A?
No. Other.
It jumps to default and prints other. Okay? But if the input were an I, it would print vowel. If it were a U, it would print vowel. So this is very useful as well. Okay? You can use it to group several scenarios of your state machine to something. Okay? And even have different instructions. You could have it like print here A or E. Okay? And if you placed an A, it would jump to this. Say A or E, vowel. Okay? But if you placed an I, it would jump to I and just say vowel. Okay? That's why this structure can be useful. It's more powerful, it gives you a lot of control, but you have to be careful with those small pitfalls. Just, if you're going to declare variables, use curly brackets. If you don't want the cases to fall through, use the break intentionally. How I write this code usually? I write case, break, case, break, case, break, and then write the code in between. Even so, it'll be easier to just write functions and just write the name of the whole function here. So it's very clear in the state machine. If state is 0, jump to execute jump 0. Execute state 0, right? Like start the game. If case equals, I don't know, in game, then jump to play game. And that way it's very easy to create a state machine. We're gonna do that next session, okay? So you can see how that works. But that's the idea, yes?
Well, you have to define the variables for the bracket.
Oh, because where is the variable value from? For that case, it was zero. And that would lead to some very strange things. If you define the same variable in all of them, they clash and it doesn't compile. If you define a variable and use that variable without making 3 cases below, you use it with the value that was in the first case and not in the last one. So it's very hard to debug. Well, if you know what you're doing, you just see, oh, I made that mistake. Okay? But if you place the brackets, the current brackets, then the variable won't exist. Okay? and you know that it has a very limited lifespan. Okay? Any more questions? No? Now we'll talk about the define. This works with the switch as well and works for several things. The first thing that you need to know is that this is an alias. I can say alias, and I don't know, 1. Okay? Whenever the compiler sees alias, it will replace it by 1 in this scenario. Okay? In this scenario, whenever I say constant name, it will replace it by value. If I say something like define pi as 3.14, I can write in my code like 5 times pi, and it will get replaced by 3.14 every single time. Okay? And this helps a lot because you could have pi divided by 2 or 4, whatever, pi, and whenever you change this, it changes everywhere. And that's very useful to keep consistency. Okay?
That's like declaring a variable?
No, because this is a constant.
Oh, yes.
Okay? It doesn't change. Okay? It's fixed, completely fixed. Good? It has several other uses that go beyond just the value. You can, let's say, and this will be interesting because you already know this. Let's say that I define the mask to be 0xF0FF. Okay? And I can use that in my code. And that would be very clear. I'm using a mask. Okay? And if you change hardware and the mask changes, you just change the code, recompile, and all your code keeps on working with the same logic. You see? That's why this is very useful. Okay? Same thing for your state machines. You define state, well, let's say gameplay to be 1. Okay? And you define wait for credit to be 0. And in your switch, you have case, wait for coin, execute this. Case, gameplay, do this. And it's very clear. And you can change the values as you add more in between. And it becomes easier to read, easier to maintain, everything. Okay? All good? We'll learn that, but you can, I'm showing you so you can tell from now on why that's useful. Okay? Here, we're going to be learning about arrays. Arrays are collections of data. They must be the same type. If you declare an array of ints, all of the elements in the array are going to be ints. Okay? If you declare an array of floats, same thing. Arrays are fixed size, fixed type. Okay? You cannot grow an array. In Python, you used lists. And lists could have anything. You could store text, you could store floats, you could store ints, and you could grow them, right? Now, they are slow because of that. If someone wants, I can explain them why. Okay, but that's a problem for computer scientists, and I teach that at data structures, different course, and we build our own data structures that grow like those in Python. Okay, but here we're coding for hardware, and when we code for hardware, we know the amount of memory that we need. Okay, in advance, or we limit it, or we define it, because otherwise we make code that's slow, and we don't want code that's slow because it makes you fail when you're doing things. Many of the things that happen when you code your firmware for your hardware is that it becomes slow because of certain non-optimizations. I'll try to show you the tricks I know regarding that. Okay, which things make things slow. Python is slow because it doesn't have fixed data types, and you'll see why in a minute. Let's talk about this and why these things are fixed size. Okay? Let's learn by example. Remember, playing is easier to understand what's going on. Okay? I'm gonna build code this. Okay? Now, I'm building an array of 5 integers. Let's change that to be a bit better. Okay? That's better because it's more readable. It's easier to read. I have an array of size, and the size can change. If I want to store data in the array, I can say for int I equals 0, I less than size, I plus plus. Okay? And then say array at I equals 0. This initializes the array to zeros. And the important thing is that I can change that to be a 512 array, changing just the define. I change the size and I change the for at the same time. That's why this is useful. Okay? Now, this is why Python is slower. This is guaranteed by Python when you create an array. It's immediately zeros. In C, that's not guaranteed. If you want to set it to zeros, you set it to zeros by hand. Okay? Otherwise, you leave it as such. Why would you want to leave it as such? Imagine that you are only storing values as they come. You store them. Let's say that that's the scenario. I say, I get data, and I say, while data, this is just a supposition, I store that data. No? If I receive a data, I say array at position equals data. And I add 1 to position, and I say if position is bigger or equal than size, there's an error. Or better yet, while data and position less than size, then I keep on storing the data. Okay? That way, I only have the data stored that I need. But going back to this, let's go back to this version of it. Okay? This is a way to retrieve and to store data into an array. If I have that, I can print the data in an array in the same way. This stores, but I could also print any value from the array. And access the data in that same manner. This is identical to Python, yes? I compile it, I run it, and the array has random data inside of it, okay? Because I didn't initialize it. All good? Only if I have initialized it to 0, again, then I'd have everything to zeros. This is, again, your responsibility on memory if you want to use it. Now, this guarantees that the array is set to zeros, but it's slower. How much slower? Per year. Okay? But this is because we only have 512 values. Okay? But it takes time, and that is slower. So we have this, and we know how to access data and how to store data into an array. Okay? I told you that arrays have fixed size and a fixed type. Let's do something. What do you expect this code to be? Let's do this. Let's change it to okay. Read that code carefully and tell me, what do you expect it to print? so it's smaller. Okay. Okay, stay up there. What happened? This is why I have always drawn this for you. You have X, and it's a place, whatever, 100, 0 if you want. Then you have array, and it starts here. What position is this? This is 4, because this takes 4 bytes, right? So this is position 4. This was 100. And then, how many blocks am I reserving when I'm doing this? 10, okay? So they are 10. Which ones are their names? They are 0, 1, 2, 3, 4. Which one is the last one? 9 is the last one, okay? How can you remember that? I have 10 fingers. If I name this 0, this one is 9. Okay? Always, because they are 10. There are 10 numbers, I have 10 symbols, but the last number is 9 because I have a 0. 0 takes up space in that context. Okay? So this goes on up to 10 times 4, 40. So this Y is at position 44. Okay? And this has a 200 stored. Now, C gives it a number and a number in between as a cushion in case you make this kind of mistake that I'm making on purpose. Okay? That's like, give it a cushion in case somebody goes big jumped. What we did when we say go to array size plus 4 is store at array position 13 and 12 and 11. I went overboard. With 11 it would have been enough. Okay? Store zeros. But what's the position 14 or 13 or 12? Let's go to something more basic. I know that the array starts at position 4. Okay? That is a pointer. It tells me where the array starts. That's how array work. When I type to scanf, I'm telling it right to the address where n is stored, a decimal number that they are giving us. Okay? So it goes to that number and places in that box. Here we have, let's say that I have array 5. What's the address of array 5? Can we tell? If the base is 4 and each one takes 4, 4 times 5 is 20 plus 4, 24. So array 5 would be here at position 24. And the same applies for array 11, which is the one that we are using. 11 is at the exact same position as Y. Okay? So we are overriding a different variable just because I didn't check the bounds of the array. Okay? I went overboard and overrode that. This is what happens in C. Let's see what happens in Python if I do this. Can somebody tell me what happens in Python if I do that? Do you remember what happens? Or wasn't there enough frustration for you with this? What happens if I do that? If I do that, Python crashes. Okay? C didn't crash, but that doesn't mean that it's not problematic. Okay? It won't crash now, but what if that variable Y was something important? I destroyed it. and the logic of my code will be completely broken. So it's an error in any way, okay? You should be careful, and that's why you never do this. You always do this, okay? All good? And if I didn't use that, and I had this coded to 10, and suddenly I changed the size of the array to 5, this will also destroy the data if I don't check every single time that the array is accessed. That's why I advise you, always use defines for the size of your arrays. That will help you for a lot of trouble. Okay? All good? Now, we have little time for what comes next, but this is just a summary of what we just saw. These slides is exactly what we just saw, but I rather showed you by example than from the slides. This is matrices, exact same thing as in Python. You have 2 indexes, and that's it. There's no magic, okay? And this is important, and this is the last topic I want to cover today. You have arrays of chars, and those are the ones that can store strings, okay? So then I can declare something like okay, and I can say okay, this is not initialized and it will have garbage. Okay? But and the %s prints a string of characters. That's what it does. And we'll learn something more about that in a minute. Okay? I can do this. As you can see, I didn't have to place the ampersand before the name because that's already a pointer. That's already an address. Okay? And this works as is. If I compile that, run it, and I say Artemio, it stores and prints Artemio. Okay? All good? Now, let's do something a bit more interesting. This is a way to print it, okay? Or store it. Let's say that I want to store a name there. Name at 0 equals A. Okay? And I do the same for name at 1, name at 2. Okay? There you go. And now I store at name 3, I'm going to store a special character. That special character is the null character. It's a character that has no value. Okay? You guys are hardware people, so I can tell you this special character is nothing more than 0. Okay? In hardware, that's the meaning of that special character. It's 0. It's a character that's not printable and means the string ends here. If I build that and use the printf function to run it, exactly. Good catch. There you go. All good? You can see how the inner workings are really happening inside of language. I tell you this because you're going to be doing this kind of thing with a microcontroller to send messages to the LCD screen.
For our case, the mechatronics is the same to write 0 and the other value do that, but in other cases.
For a computer scientist, I would flunk them for doing that. Because, why? Because that value can change in the future. It won't, I mean, but they can change it. You have no guarantee that that value will always be 0. Okay? Now, how does that work? Imagine that you don't have printf, okay? How would you write a function that prints a string? What would you do? let's say that I write a function that's called print that takes a pointer to a string. And what do? I create a variable that starts at 0 to keep our position, and I ask, while the string at position I is not 0, print whatever is at position I. Okay? And this is how print works. I didn't scanf, printf, yeah. Print and oh yeah, I sent it %s. I should send it name. Okay? It was doing exactly what it was told. There you go. That's how print works. Okay? Again, I want to show you this so you are not afraid of the internals of things, because you'll be going into the internal of things when you write code for microcontrollers. Okay? This is how printf works in a very rudimentary way. Okay? But this is exactly what it does. It just goes one character at a time and prints it. That's it. Okay? I left you an exercise in the slides so you can practice. Based on that, here you can create a menu and have different options over strings to practice on arrays, strings, and all that we learned today. Okay? Good? Well, see you on Tuesday.
¿Cuándo será el próximo quiz?
El próximo quiz va a ser el viernes siguiente. Okay?
La semana pasada
Lo hubieran dicho antes para cambiárselas luego. Perdón, que no se los cambio de una vez.
¿Desde aquí te vas a pegar? No, pues me va a decir.